Hi guys, thanks a lot for the invitation and for the nice presentation. So yeah, I will talk about a work that is not the work I've been doing during my PhD. It's a recent work I've done with a wonderful PhD student at Mila who initiated the project, so deserves much of the credit for this, some of this. And I'm going to talk about a way to solve PDEs, or partial differential equations, with machine learning, the so-called neural PDE solvers. We'll see what it is soon. Of course, it doesn't work.
I think you need to point it
Oops.
to be closer.
No,
okay.
perhaps is. Sorry, good second. Just
Yeah. Wonderful. Thank you. Right. So, yeah, what are partial differential equations? Also known as PDEs, and ODEs is short for ordinary differential equations. So they are everywhere in science. They basically describe the evolution of a system. So it can be anything from the simple to the most complex. Some things we don't really know how to model them perfectly, but it's like a nice proxy. So let's say something like weather could be defined, could be modeled with like Navier-Stokes equations and like other equations, heat dynamics, a simulation of a crash, a design of a plane, fluid dynamics, everything can be modeled with PDEs. So if we manage to have a way to solve PDEs very efficiently, it would be very nice. What is a way to solve a PDE classically? So first, what is a PDE? Is basically this system of equations. The first one is just it defines basically the relationship between the temporal derivative and all possible spatial derivatives of your solution U, and then the space vector X and time T. And you have these two other ones, which are initial conditions and boundary conditions. So where does it begin in space and when does it begin in time, basically? And the general case can be very difficult. Actually, these two conditions can make the problem possibly intractable or very difficult. And depending on the PDE, it can be very difficult to solve analytically. So we use numerical solvers, which are basically as follows. What we do is it's not what I do, but what people have been doing for PDEs is kind of, finite element methods. So you can partition space and time into a grid, and then you can try to estimate the spatial derivatives with like finite difference, for example. So you estimate the derivative locally in a discrete manner. And then you can use spatial derivatives to make a time update. And basically you go back to an ordinary differential equation instead of having a partial differential equation. It's like, when you solve like a non-linear problem, you try to get back to a linear problem. In the PDE world, you want to get back to the ODE because it's just much easier to solve and you know exactly how to solve it. So this is the classical way.
I'm so sorry, Dan. Can I ask you to come on this
Of
side,
course.
please? Otherwise,
You don't
people don't
see me.
Yeah, the camera doesn't go with that direction. Thank you.
You think people want to see me? Yeah, it's okay. Thank you. Alrighty. So yeah. So why using machine learning for this if we can do it with numerical solvers? So the problem with numerical solvers is, well, they are very compute intensive. They might, depending on the resolution as well, and I will talk about resolution later because it's key, they might take a long time. And you have to rerun them every time you have a new PDE, or if you have a new initial condition, new boundary condition, etc. You have multiple method of lines, finite differences, volume methods. So for example, for weather, a lot of people still use these, but it just takes a long time. Why using machine learning? It's nice because if you have the data from classical solvers, that's the thing, you still need the data generated by the classical solvers, and then you can learn how to estimate the solution, and then you don't have to do it again. It's basically faster. You can learn the solution directly from the data generated by classical solvers. And there are ways to kind of create new data, to augment the data from the classical solvers. So yeah, it's still faster, and you don't have to retrain the model for solving PDEs with in distribution parameters. So basically, in the last 2 years, I would say there is kind of a hype in machine learning for trying to do this. neural PDE solvers. There are multiple state-of-the-art. At the time where we were doing the paper, that just came out at the end of last year, but things go very fast. Now there are new ones. But at the time, these are our two competitions for irregular grids, meaning not just like a mesh of pixel, but just for any kind of arrangement of points. There's a method called message passing neural PDE solvers that use graph networks heavily and a few tricks that I won't go into details. And for regular grids, there is something called neural operators that was created to basically try to estimate the solution of a PDE directly from the initial condition. So you learn the operator that maps the initial condition to the solution of the PDE. And it's very efficient. And in this case, it uses Fourier analysis. So you pass by Fourier domain, you just select the few first frequencies, then you pass back in the original domain, and you have multiple layers of this. This is deep learning, so you just stack layers, and it works. When it came out, it made like a lot of noise. The problem is they're not very good with resolution. So what I mean by that is they have some super resolution capabilities, but not so great. And the problem is with numerical modelers, like for example, the weather. This here, ERA5 this is the entire world. Imagine, this is the US, this is Africa, this is something like pressure on the entire world. So if you want to simulate this, you have to, depending on what you're looking for, the resolution can be more or less coarse. But if you want something precise, it's difficult because the numerical modelers, usually they're like 3 to 200 kilometers on each side of weather models. And if you want to zoom on a place, it's very difficult. So what we would like to do with this method, and what motivates this entire thing, is we want to be able to predict the solution at any point of the space you consider, anywhere, without relying on a specific grid, and without relying on, of course you rely on the points where you have the solutions, but you want to be able to interpolate to anywhere around. And the good thing is, intuitively, if you do this, it might allow you to do what we call zero-shot super resolution, which is that you can predict directly the solution for a higher resolution than the one you're training the model for. So in this case, we managed to train the model in like a 64 by 64 grid and apply it directly to a 256 to 256 grid, which is very nice because then you don't have to, train on the higher grid. It takes more time, etc. Note that there are some people that do machine learning to just do this super resolution. So they train using the high quality and the low quality, and they try to map between the two. So in this case, it's good because it kind of gives you a shortcut. But how do we do this? So in this slide, basically, I'm going to show the entire kind of architecture of the network. So again, this is deep learning. So it's just, you can see it as Legos, like it's a lot of different networks that we apply one after the other. And then we're going to, back propagate through all of them to tune the parameters. So I'm going to show step by step the architecture with kind of the small input-output equation for each of them so that we can follow a bit more formally. Okay, so we start with, these are points that define our grid. Okay, it may be regular, it might be irregular, meaning it might be pixels or it might be non-regular grid. We separate from points where we have the solution in the past, okay, that we call the parent mesh. So these are locations that we have, and these are special queries. We're going to use these special queries. So these are new points where we want the solution to be able to train the model. Okay, so the first thing we do is we use an encoder, which is done like everywhere now in machine learning. So basically, you want to try to encode the information, in this case of the PDE solutions known in the past. You have this, like the little transparent circles there means that you have like multiple frames for the solutions. You want to encode this information, usually in a smaller dimension, using an encoder that can be, for example, a convolutional neural network, or a graph network. We use the two. The second one allows you to kind of avoid the regular grid. And yeah, I try to keep the colors to match the equations and the thing, but it doesn't matter that much. Basically, the K denotes the time, okay, and the J denotes the position. So PJ is the location. ZK is the embedding at position PJ at K's frame, and you apply X data, which is the encoder here, which is a neural network, and you obtain your encoded information of the past PDE solutions. Okay, so now here you're in a latent space that might not have physical sense, but where the information is kind of condensed in a way that it might be better to learn from. Okay, and that is the main thing. That is the main module, the main contribution to the whole paper. Really, what we want to do is then you want to cross. So still in latent space, you want to cross the spatial queries with the parent mesh embedding, and so in both spaces, the original space and the latent space. And basically, what we do is we say, okay, for the new locations, we're just going to take the nearest neighbors and apply a neural network to it to try to predict the solution here of the spatial queries at all the past frames. And for this, basically, you just have this G theta here is a fully connected neural network, also known as multi-layer perceptron. We just take as an input both of these solutions in both spaces. So this is the embedded one, this is the original one, the distance between the points, the time, and you just do like a weighted sum, right? So the weight is just proportional to the distance of the points of the nearest neighbor, and you feed that to another neural network, okay? So, the kind of the theory of deep learning is if your neural network is expressive enough, it's big enough, you can kind of learn anything. So that's the idea here. You want to be able to learn the correlation between the nearest neighbors and the spatial queries. Okay, so at this point, you have the solution for the past frames of your PDE for everywhere, your parent mesh and your spatial queries. So now you need to predict in the future. So we separate basically the interpolation and the forecasting. For this, we first build a graph that encodes all the information and that fuse together the information about the parent nodes and the query nodes. You fuse into a graph. So of course, the weights of the graph, the edges, have the information of the distances and of all the correlations between the points. And then on top of this, we have a forecasting module that is a graph network that predicts for all the points at all the locations, the PDE solution in the future. Okay, and for this, we actually use a very, very powerful network that we took that is called graph neural network is a thing that has been done for a long time. And it's a team at DeepMind that worked on graph networks for physics to try to simulate the physics as good as possible. But this is our method. So basically, we reuse this forecasting module here, and we take the encoder to use it here. Okay, just because this is deep learning, we obviously need some losses because this is all trained by gradient descent. So it's pretty straightforward. We have two losses: the interpolation loss here that just encourages the interpolation to be good. So basically, we want to predict here. We have learning points for this. So we want to be able to interpolate in a good way, and the forecasting loss that will act on the last part to verify that we forecast well with respect to the observed future frames. Okay, and then the loss is just the sum of the two. We could have put weights. It actually works pretty well without any tuning of any weights in front. And this is the method. Very quickly, because we use this graph network heavily, I want to pay homage to this work by some guys at DeepMind. So this is just a figure I took from the paper. So why using graph networks? It basically embeds correlations between all points in space through different nodes, and through an algorithm called message passing, it propagates the information. So you can have multiple layers of this. through the nodes of the graph, okay? And it can learn and predict dynamics. And because of this, you don't have to rely on the regularity of the grid anymore. And you can note that we took inspiration from the form as well, because for each, basically, they try to model physics. So in this case, it's just like a discrete representation of a liquid in a cube. They try to learn the simulator at each step that goes from step k to step k+1, and they separate this process into an encoder, multiple steps of, so the encoder puts it in a graph form, multiple steps of message passing that basically propagates the information to the nodes, and then a decoder that predicts in the future. And yes, we use this at 2 places in our architecture. Okay, so this is the method. For the results, we used Berger's equation, which is a typical PDE that people use for this kind of experiments. It's basically like a wave equation with diffusion. So it can be seen as a simplification of Navier-Stokes equation. It's just, we took this data because the competition was using this data, so we wanted to compare. And in 2 cases, so we took multiple different scenarios, so with multiple different values of the parameters, and we have a 1D case and a 2D case. Maybe we could do a 3D case, but it takes like a lot of compute.
I have a question.
Okay.
What is the need? You can ask me later on also, but why is there a periodicity need of periodicity in the space? Because there is sine and cos curve.
Yeah, no, there's no need of periodicity. It's just, this is the initial condition. It's just like,
Okay.
it's just yeah, it's just a sinusoidal initial
It
condition.
can be anything.
Yeah, it's just a typical thing used. Right. You might ask, what is regular grid? It's a bit weird to work with regular grids. Basically, what we did to have like kind of a simulation of an irregular grid, we just took a regular grid and like erased some of the points. And in this case, for example, you have 2 different modes. This is uniformly distributed. This is distributed according to a Gaussian distribution. So in this case, and for everywhere, the blue points are the spatial queries. It's just, we take a regular grid, basically. We take out some of the points to make it irregular. We select some of the remaining points to be the spatial queries, and the rest are the parent mesh embeddings, okay? Depending on the number of points, you might have something that is more or less dense. And you see here for like the Gaussian version, you see more what's happening when you have more dense points. You have, this is like the bell curve here, and you have more sparse around. We just wanted to take different scenarios. Okay, so these are the results for first 1D experiments. The top is regular grid, the bottom is irregular grid. We try the 2 versions of the algorithm, which is the MAgNet, the CNN version, where the encoder at the beginning is a CNN, a convolutional neural net, and one where it's a GNN, which is the encoder part of the graph network from DeepMind. And we compare it to the further neural operator and the message passing neural operator. Okay. Note that the FNO is not made for irregular grid, so we cannot really compare with it. It's not fair. But the MPNN is supposed to be pretty good for it. So quickly, these are the results for the regular grid on top and the regular grid on the bottom again. And you can see here, these are test resolutions down because we want to do super resolution. That's the whole point of the method. And on the y-axis here is MAE, it's the mean absolute error. So the smaller, the better, of course. The train resolution is 50 by 50. And this is 50 by 50, 100 by 100. I'm sorry, it's a bit small. But basically at 50, it means that it was trained on a resolution and predicted for the future on the same resolution. It's quite similar for all the models. But you see that when you increase the resolution, so it was trained at 50, you want to predict directly at 200 by 200 mesh, then suddenly MPNN, which is here, is really doing poorly for this E1 dataset, which is one of the datasets, and we do better for this one. Note that this is under resolution, so it's a bit of a weird task, but we still do better in this case. And same here, and in here you have like a great resurgence of FNO, which for some reason it does better here. That's the, sometimes you don't really know what happens. But you'll see that our method is not the best for all cases. This is for irregular grids. In this case, you have the training resolution here and the testing resolution here. I'm not going to go into detail. Basically, the bold values are where the best MAEs, and in most cases, basically we do better in 1D. This is 2D. This is a 2D case for regular grids. So again, here is the training resolution. So that's why you have like a dip. So we train in this case in 64 by 64. And the same here. This is two different data sets. And you can see that here on a regular grid, these are hours. But actually the MPNN is doing a little bit better when you go up to the 256. And in this case as well, it does a little bit better. We realized actually that our thing was really working better with irregular grids because it was taking advantage of the graph neural network and on the interpolation between the points. So these are the results for the irregular grid. Yeah, it's a bit dense, but basically the idea is these are two different data sets again, two different modes, but it doesn't matter. Let's say we focus on the first one. The 4 blocks are different training resolutions. And then here you have different testing resolutions. Okay, so the more you go up there, the more you have information when you train. And the interesting thing is that we realize that with our method, it's still MAE now. Basically we achieve better results when you have less data to train from. So if you start from like a low resolution, like 64 by 64, and you try to apply it to a higher resolution, it works better. The MPNN error kind of explodes, and we do better. And as you move to a bigger training resolution, actually the other method does better. So, there's a trade-off. There's no winner. It's interesting to see that because of the interpolation capabilities of our method, the less you give, the better it performs, when you compare it to other ones. Some visualizations. So this is in 3D where the y-axis is time. Just to be able to visualize, these are different resolutions. So this is the ground truth. This is our method, and these are the two others. So you can see that in this case, we'll be able to match it pretty well. There are some artifacts somewhere. Sometimes it varies. But usually in 1D, we do a really great job. In 2D, not always. So especially the CNN version, which is the non-graph one, kind of struggles. But the GNN version does pretty well. Okay, and then if you want to see other visualizations, there's like a lot in the paper, just to have kind of more things to see. This is on an irregular graph. So it's a bit harder to predict. Again, the top is the ground truth. You might have some artifacts here and there, but you're doing a pretty good job. Okay, and I'm going to finish. Hopefully, we have time for questions if you want. So, yeah, we developed a method that really wants to work on irregular meshes and do super resolution. It works very well for irregular meshes. For 2D, it seems to be struggling a little bit more. Yeah, we have a lot of ideas to improve it, try to improve the temporal horizon, try to generalize it to different geometries with spatial boundary conditions. You can try to, on the tail of a plane or something. Some people do crazy things. That's it. Thank you, guys.